All right. Yeah. And as I mentioned, we'll moderate questions from students or attendees, or if you see them and you want to answer it, go ahead. So,
Okay, sure.
okay. So yeah, go ahead.
All right. Hello, everybody. I'm Tsung from the University of Utah, and my research makes static timing analysis faster so designer can more efficiently analyze and optimize the timing of their circuit. Today, I'm very happy to show you GPU accelerated static timing analysis that can achieve new performance milestone previously out of reach. Let's see. Static timing analysis, or STA, is a very important step in the overall chip design flow. It is a key component in modern VLSI design because it verifies the expected timing of the circuit and ensures correct functionality after tape out. The term static means we do not consider the input vectors, the Boolean value of each pins, but the best case and the worst case delay and timing value of each node in a circuit network to analyze. For example, we may just consider the minima arrival time of a node. What is the earliest possible arrival time at the node? Or the maximum arrival time of a node? What is the latest possible arrival time of a node? By figuring out the best case and worst case timing value at each node, we can quantify the violation based on the timing constraint under the given clock frequency. So this process is indeed very challenging because circuit graph is very large, billions of transistors in today's VLSI design, which means we need to analyze millions or trillions of critical paths, and that is often exponential number to the circuit graph size. There are two fundamental checks in STA. A check is nothing but a timing constraint. We need to see if any data path violates the timing constraint. The idea is, the modern circuits are sequential. Digital circuits are often sequential. We have a clock to drive the data path and flip-flop to capture the data path. Everything happens synchronously with the clock. Well, this means the data must arrive on time. You cannot arrive too late after the clock or too early before the clock. So this property gives us the timing constraint. We have modeled the required arrival time for data at each sequential component, like a flip-flop. We have the minima required arrival time, and that is the hold time after clock. We also have the maxima required arrival time, and that is the setup time before the clock. Data needs to arrive in this min-max interval, required arrival time interval, defined by the timing constraint. If you arrive too early, you have the hold time violation. If you arrive too late, and then you have the setup time violation. So that's essentially how STA is going to do to check whether you have violated any timing constraint. This type of timing check is indeed very similar to the traffic light analysis. On the road, we have multiple traffic lights. Cars can only move on green, and we must stop on red. Of course, I know some people don't, but basically, we want to make sure the car can pass a block before the next red light in most situations. And each car has a delay related to its driving speed, right? So this analysis is like a question: can I pass the block before the next red traffic light within this speed, 40 miles per hour? Building a good traffic system is very complex and it's very challenging. Imagine how many roads we have in the US and how many traffic lights we end up with. We want to make sure every car can follow the rules. Same for STA, static timing analysis. It's very computationally challenging. A primary cause is the large circuit graph size. Today's circuits are very large and very complex. We have millions of gates or even billions of nodes and edges in the circuit network, and we need to propagate computer timing along this giant circuit graph. Here I'm giving an example of a IBM circuit design released in ISPD, and that composes 10 million gates. The model STA timing graph is very complex, and a signal path, a data path, can span pretty much the entire circuit layout. Completing a full timing on this very large circuit can take more than 8 hours with the 800 gigabyte memory. So we need computationally efficient algorithm to accomplish the timing analysis. So To address this challenge, we have developed a tool called OpenTimer. That is an open source STA engine. In OpenTimer, we introduce a bunch of new algorithms and data structure to handle a number of STA challenges. For example, we introduce a new API concept to facilitate the parallelization of incremental timing. And we are able to achieve new performance and scalability milestones that were previously not possible. And OpenTimer, a key part in OpenTimer is everything is designed in mind of the parallelization challenge of STA. Parallelism is never an afterthought in OpenTimer. And right now we have two versions, V1 and V2. And the difference between the two versions is the parallelism we use. In V1, we use OpenMP. And V2, we switch to an open source project, TaskFlow, using task parallelism. The key idea of our OpenTimer engine is we leverage manycore CPU parallelism to speed up the analysis runtime. We can achieve, in most cases, dramatic speed up using 8 to 10 cores or threads. However, scalability saturates and stagnates at about 10 to 16 cores. And this is quite consistent for most existing timers, including commercial tools like Tempers in Cadence and PrimeTime in Synopsys. When we compare OpenTimer with other timers, we found most timers saturate at about 10 to 16 cores. For example, here we have a runtime for a full-time update on a median gate design using one CPU. It takes about 200 seconds to finish. With 8 CPUs, we can reduce the runtime and achieve 4 to 8x faster. However, after 16 core, the runtime does not improve anymore. There are many reasons for this. Well, first, we know Amdahl's law, and that limits the strong scalability of the algorithm on a parallel architecture. The maximum speed up you can achieve is proportional to the part you can parallelize, which makes sense. Also, the circuit graph, the structure of the circuit graph also limits the maximum parallelism. For example, if the graph has only 10 parallel nodes at most, you cannot get 40x speed up. Irregular computation, because STA analyzing the timing on a circuit graph, require a lot of graph-oriented algorithm. A lot of computation happen on the graph. They are not very cache friendly. It's difficult to fully utilize the memory and saturate the bandwidth of a memory to achieve dramatic speed up unless we change the data layout. So after several years of research, we arrived at a key conclusion. We need to incorporate new parallel paradigms to speed up STA. One particular direction of interest is graphics processing unit, or GPU, because we believe GPU opens up many new opportunities that can speed up STA with transformational performance milestone. And we have seen several evidence in the EDA and the CAD that has leveraged to achieve dramatic speed up. For example, 100x speed up reported in logic simulation, and 20 to 80x speed up reported in placement using GPU. Before we talk about how we use GPU to accelerate STA, I want to briefly show you the difference between CPU and GPU. I know some of you may already know what a GPU is, but just in case you don't have much experience with the GPU. CPU is built for compute-driven or compute-intensive applications. It has a few powerful threads to compute critical blocks very, very fast. GPU, on the other hand, is built for throughput-driven application. GPU has many lightweight threads to compute a huge amount of data vectors at one time. Well, each GPU thread is very lightweight compared to the thread concept in CPU. And some of the GPU threads do not even have a private stack. But multiple GPU threads can work together to compute a block of data in a single or the same instruction. So this is a diagram that compares the architecture between CPU and GPU. And as you can see over here, GPU has a many, control ALU units to compute the data, and it has relatively small control units and a cache size compared to CPU. So probably it's better to understand the difference between CPU and GPU using this cartoon. Because of this architecture, CPU is very good at running graph algorithm, irregular data structure, and anything that requires dynamic branch and lots of control flow and so on and so forth. GPU, on the other hand, is very good at computing regular patterns, such as matrix operation, gaming, video processing, and other applications that heavily rely on linear algebra, because most of these applications use a similar instruction, apply similar instruction or the same instruction to a bunch of data. For example, multiplying two vectors and adding two vectors and so on and so forth. Now we have a basic understanding about GPU and its unique advantage for data-driven computation. I'm going to show you how we leverage the power of GPU to accelerate STA. Before we dive into the real part, is any question from the audience so far about the motivation of the talk? Okay, good. So let's move on. We target two important STA steps: graph analysis, graph-based analysis, GBA, and path-based analysis, PBA. Generally, we model the circuit network into a graph. Each node in a graph represents a particular pin in the circuit graph, and each edge represents a connection between gates in the circuit graph. The main job of GBA, graph-based analysis, is to find the timing value of each pin, the best case and the worst case of the timing value at each pin. For example, what would be the fastest arrival time and the latest arrival time at each pin? Because it only considers the best case and worst case delay value, GBA introduces lots of pessimism. After GBA, we have a graph of updated timing value, so we can query this arrival time on best case and worst case, even though it has a lot of pessimism. So we typically run PBA after GBA. We want to analyze, identify a set of critical paths and analyze those critical paths from an updated timing graph, path by path, and apply path-specific update to remove those pessimism. And I will talk about those details later. Both processes are important steps in STA. And our research goal here is to speed up GBA and PBA using GPU and achieve significant performance scalability gain beyond CPU parallelism. Now, I'm going to talk about our recent work of GPU accelerated static timing analysis. This is a work published in ICK last year and target on graph-based analysis using GPU. Before we offload STA to GPU, we need to know our enemy to attack. So we break down the GPU runtime of OpenTimer on a large design, Leon 2. As shown in this figure, what we found is that the runtime bottleneck in the STA happens in the RC delay update, the green bar shown here in this figure. Almost 48% of the entire runtime is taken by RC timing update. And this makes sense because the RC network, the connection between gates, is very large. The next critical part is the preparation step, or to levelize the circuit graph into a 2D level list so we can propagate the timing level by level without breaking the dependency. This step takes about 42% of the runtime, which is very huge. And this is because we need to traverse the entire circuit network and figure it out. Yes.
Can I ask you a question? So what do you use for the cell delay models? Are you using like a current source model or just a voltage-based model? Or
so right now we use nonlinear delay model, and I will talk about that later. Yes, that will be covered in the later slides. Okay. So there is another relatively small portion, 10% taken by the gate delay update, and like I said, we use a nonlinear delay model to calculate the delay through gates. And this slide shows the overall algorithm flow for our GPU accelerated GBA. We implement our algorithm on top of OpenTimer, and this figure shows we offload the levelization, RC timing update, and the gate delay update on GPU. These are the three tasks, the most time-consuming tasks in GBA. Other tasks such as backward propagation to compute the required arrival time remains on CPU because their complexity and data size are fairly small. There's no benefit from doing that on GPU. So the first step in a GPA is to levelize the graph because we need to keep track of a dependency between different nodes. We cannot propagate some timing value before we calculate, before we know, for example, the slew or the arrival time from the previous layer. So there is a dependency between the timing propagation. Levelization is a widely used method to parallelize the STA. It's often a preparation step for timing propagation. We build a level by level dependency for propagation tasks and this accounts for 40% of the runtime if you run it on CPU. Tasks within the same level can run in parallel. Lower level tasks must not run after tasks at a higher level. Okay. In most timer, levelization is accomplished by a single CPU thread because it requires a graph traversal, and that is very difficult to parallelize using a CPU thread. So we do this parallelization on GPU this way. A set of nodes called frontier is maintained in our algorithm, and they represent the current set of nodes we are dealing with. They are essentially the nodes at the same level. The initial frontiers are nodes that do not have any input edges. Of course, that makes sense. No dependency. Well, each time we can obtain the next level of nodes and by doing this expansion from the current frontier over and over. So if you have multiple fan-in, in our case, like this node G and H over here at the third level, you may reach the same pin, in this case, the pin E, multiple times. So here we use the atomic operation to collect the next level node only once using GPU. There is one thing to note. We do this levelization backward. We start from the primary output and levelize the graph all the way to the input. Okay, we start from the primary output and levelize the circuit graph all the way to the input. We do not do forward levelization because we observe for most of the design, the output degree has a higher divergence than the input degree, as you can see in this table. This is indeed caused by the RC network, and RC can be very huge tree. Most RC networks are very huge tree. They connect to multiple gates and result in very high fan out. The distribution of a degree impact the performance of our GPU algorithm because the higher distribution, higher divergence of the input degree will introduce unbalanced load on GPU. And load balancing is very important for GPU computing because it's better to have all the threads run the same thing at one time. So we do this levelization backward from output to input. And based on our experiment, the performance difference can be up to 15%. After levelization, the next step is to do RC update. We calculate the delay through each net. A net is a connection between gates. In a circuit graph, we can have different gates like AND gate, OR gate, and they have to get connected to each other through net or wire. Okay, so that's the delay that happens at RC net. So here we use the famous Elmo delay model to compute delay through a net. And Elmo delay model is essentially a linear dynamic programming algorithm on tree to compute a delay. It has two phases. Phase one to compute a cumulative load using an upward traversal. Phase two to compute a delay based on cumulative load from phase one. I'm not going to explain all the details about Elmo delay, but I'm trying to highlight the basic idea of how we leverage GPU to compute these two phases on a tree structure. The key idea here is a traversal. As you may know, it's not easy to perform depth-first search on GPU because depth-first search is recursive and stack-based. It's not very GPU friendly. Instead, we flatten the RC tree to a sequential sequence of nodes. Every parent appears before any of its children. And this can be done in advance on GPU by running a parallel breadth-first search through a counting sort. For example, here I have a RC tree of 6 nodes and 5 edges, Z, A, E, B, D, C. for a tree structure, the number of edges is one smaller than the number of nodes. We flatten this RC tree to a linear array of this order, Z, A, E, B, D, C, such that if you look at this order, the parent of each node appears before its children. After this flattening, we can easily perform breadth search to traverse the tree from the leaves to the root. For example, over here, we can iterate each node in the tree in this order. C, D, B, E, A, essentially is a reverse order of this sequence, okay? And to compute the cumulative load of each node. And this can be done by one GPU thread, okay? Similarly, once we have cumulative loads ready at each node, we can do the same thing to compute a delay based on the cumulative load value. But this time, we will start from the top level to the bottom level. Well, essentially, you can already guess, we just need to traverse the sequence in a different direction. For example, we traverse each node in the tree based on this order, A, E, B, D, C. And we can compute a delay based on its parents' cumulative loads using the AMO delay model. Okay, so the key idea is to break the depth search into a flattened data structure so we can run breadth search-like computing, which is more GPU friendly to compute the tree-based model. So this is how we use GPU to compute the RC update. There is one thing we need to keep in mind, and that is the memory access pattern. On GPU, we don't have this false sharing issue like CPU cache, but we want to have an adjacent thread access consecutive memory pattern. So this is the so-called coalesced memory optimization specific to GPU. To enable coalesced memory, we arrange our data structure in a very spatial way. For every net, the computation needs to be repeated 4 times across early, late, and rise fall. In STA, we consider the worst case timing value. So there is an early and late for each value. And we are talking about digital circuit. So the domain is 0 and 1. So we have rise and fall for each node. So there are totally 4 independent conditions we need to consider for the same RC update. In our data structure, instead of putting these 4 conditions separately, like many CPU algorithms do, we need to group each condition together so an adjacent thread can emit an adjacent memory access pattern. For example, assume each early, late, rise, fall condition here takes 3 nodes to compute. And we know the number of nodes is consistent for all the 4 conditions under the same RC tree because you don't change the structure of RC tree. You just calculate the timing on different conditions. So we can group the 3 nodes to the same condition together as we draw out here in the figure. So like here, I have 4 nodes, 1 grouped together, so the GPU thread can submit the same memory access pattern during the upward traversal and downward traversal to calculate the RC update. So that's the second step of the GPU accelerated RC update. Any questions so far from the audience?
No, one thing that I didn't see, and maybe I missed, how do you parallelize the leveling of the graph, the topographical sort part?
Well, it was essentially step number 1.
But
you mean the levelization of the graph?
No, once you have levelized, I see that you do, but how do you on the GPU? You will have a lot of divergence.
So we do this level by level. We do this level by level. So we start from the first level. They do not have any precedence, and we use multiple GPU threads to expand the nodes to the next level. So let's assume, for example, at the first level you have 10 nodes, and then we use 10 GPU threads to expand.
You're not gonna have, but you are not gonna have much coalescing and not a lot of threads in this case, no? Well, I guess as it kept expanding, you might have more threads.
Yes. I mean, this depends on the circuit structure And we do have a optimization, but I did not talk about that details. We do have the optimization that tries to maintain collapsed memory access during the levelization. And
So
one important, yes?
Yeah, you are going to show later the speed up in each one of the steps, more or less?
No, I'm not going to show
Okay.
that. Yeah, because it has so many details.
Okay.
But you can definitely check out the paper.
Okay.
Okay, so the next step is to calculate the cell delay. We know in a timing graph, we have two types of delays. The first delay is the delay through net, through wires, the connection between different gates. And the second type of delay is the delay through a gate, NAND gate, OR gate, or inverter, so on and so forth. For the cell delay model, we use the nonlinear delay model, and that is a widely used model in STA. Of course, there are other models like a CCS, and which is something that we are working on right now. But I'm not going to talk about that in today's discussion. And this nonlinear delay model uses a 2D lookup table to compute the delay through a gate based on two values, the input slew and the output load. And we use this linear interpolation to compute the slew on one axis and the load on another axis, and then use this two value to derive the final delay. And because there are not too many, because there are many gates at each level, we can offload this calculation of a batch of gates to GPU, so we can compute many gate values at the same time. So we just learned how we leverage GPU to accelerate graph-based analysis at 3 steps: levelization, RC delay update, and gate delay update. Now I'm going to show you the experiment. We implement our algorithm with C++ and CUDA on one NVIDIA GPU, RTX 2080 GPU card, and 40 Intel CPUs. Here is the execution parameter for our GPU kernel. And I'm not going to dive in this because the parameter can be tuned at different GPU architectures. But essentially we have 4 kernels, one for RC tree flattening, levelization, delay calculation, and cell delay computation respectively. The overall performance is shown in this slide. We compare our result with OpenTimer, running 40 CPU and evaluate the runtime on Tau 15 benchmark. And because small circuits do not have much benefit with the GPU, and they run very fast already, so we only consider large circuit benchmark of more than 20K gates. In this table, you can see generally our algorithm with one GPU is faster than CPU-based OpenTimer at all benchmark. And the speed-up value is more remarkable on large design. For example, on Leon 2 over here, we have about 3.x faster. On Leon 3 MP, our runtime is about 3x faster. So that's the speed-up gain from the graph-based analysis using GPU. And here's the runtime breakdown. It shows the reduced runtime for each critical part of the graph-based analysis. Apparently, the most of the runtime is taken by the RC update. So in this example circuit, Leon 2 that has 21 million nodes. With one GPU, we can reduce the runtime of RC update, the orange part over here, from about 5 seconds to 1.9 seconds. So the other part that is also significant is the levelization. For example, levelization using GPU right now, the runtime for levelization is reduced from 1 second to about 41 milliseconds. We also see a significant gap between the GPU runtime and CPU runtime. This slide plots the runtime value at different number of CPU we use to run our algorithm and OpenTimer. But keep in mind, we also have several tasks run on CPU. So increasing the number of CPU also make our runtime go faster. Regardless of the number of CPU we use to run the timer, our runtime is always faster with one GPU. And you can see our runtime of one CPU and one GPU is already very close to the OpenTime's runtime of 40 CPU. And this significant performance improvement is not possible without the use of GPU. What about the effect of the problem size? We know GPU is good at processing a large amount of data at one time. If the problem is small, we don't benefit too much from the use of GPU. Here we did an experiment to measure the runtime at different problem sizes and see what are the problem size that we can benefit from the GPU parallelism. Well, this number is of course case by case. Different circuits and different GPU may have different threshold. And based on our experiment on widely available open source benchmark, we observe significant benefit from using GPU for the following situation. If the number of nets is larger than 20K, or if the number of gates is larger than 50K, or the number of tasks you need to update per iteration is larger than 15K, then GPU can come into play. Okay, you can get some benefit from using GPU. And of course, the benefit will become larger as you increase the problem size. So this number can be a good threshold to measure when to use GPU and when to use CPU for running STA, especially in the incremental optimization loop. So that ends the GPU acceleration for graph-based analysis. Any questions so far before we move on to the next topic of path-based analysis?
Actually, I do have a question about so the models I mentioned before, the current source models are one thing, and then also for interconnect, they frequently don't do Elmore delay model. They do other higher order models.
Yes.
How would that change this?
Well, I would say different model, definitely you need to have different GPU kernel, right? But one thing that doesn't change is you always need to have a GPU efficient data structure. And for most of this RC model, you are going to work on tree or other tree-like data structure. So even though right now we target on a very simple Elmore delay model, but the idea of the for example, we flatten this tree into this GPU-friendly linear array can be applicable to other model. And that is something we are currently working on right now. For example, the CCS model. That is something we are trying to use the GPU to accelerate the process.
And then one other question about, you're basically working on a single corner, right? So what about multiple corners?
Yeah, we can do multiple corner.
That's kind of the trivial case, right?
Yeah, that's very trivial because you just have a different libraries and you can glue them together. But they require another change of a data structure. So that's something that I'm going to highlight in the conclusion. So basically, if you want to have a fully GPU accelerated STA, we need to redesign a lot of data structure from the very beginning, because the data structure, data layout you use for GPU and CPU is completely different. It's completely different. Okay.
I've got a quick question.
Sure.
So I'm coming at this with maybe a different background in that I don't know much about these circuit graphs, but I do know about doing sort of BFS and SSSP on GPUs. You know, a lot of times those algorithms, the performance characteristics change a lot depending on the input graph. You know, you're going to do different optimizations for a road network versus a social media network. And so in your analysis, like when you get these circuit graphs, how much does do the optimizations you apply, how much do they depend on the actual graph? And are your graphs sort of similar enough that you are confident that this works across a lot of different graphs that you're going to get?
Yes. So the question is, how does the property of the graph affect the design of our algorithm? Indeed, a lot of our algorithms are designed based on the consideration of some spatial property of the circuit graph. For example, most of the graph we target do not have cycle, which means we can have more spatialized like a dynamic programming to run the shortest path. And the other consideration we have is, if you look at the circuit graph, it's not going to have too like high fan in or high fan out. Most of the time, the degree of the input and output is limited to 8 to 10. So that means we can have more, region to play around with the spatially designed data structure for GPU. And this indeed is one of the topics I'm going to talk right now, to generate a path.
Okay, yeah, I mean, that makes sense. In our work, with social media graphs, sometimes you have massive fan outs. And if you have a fan out of more than 32, then it makes sense to do that fan out within a warp on the GPU. But if you have lower fan outs, then you might not do that.
Yes, yep. So for most of this circuit graph-based analysis, we need to consider some spatial property of the circuit graph, and we can use that to design our algorithm. Yeah, this is something that I'm going to talk about right now.
Great, thanks.
Any other questions before we move on? Okay, good. Oh, thanks for the question, by the way. That's very helpful for us to refine our algorithm and do some more research. So right now, as we described in the beginning, STA has two important steps, graph-based analysis and path-based analysis. Graph-based analysis outputs an STA graph with updated value, but the result is often too pessimistic because the graph-based analysis only consider the worst case and the best case delay values, okay? To remove this pessimism, there is another step after graph-based analysis, and that is the path-based analysis. The idea of a path-based analysis is to identify a set of critical paths from an updated graph. And this process is extremely time-consuming because of the exponential number of paths in the circuit graph you need to analyze. Once you identify a set of critical paths, you can perform reanalyze each path with path-specific update. For example, you can repropagate a slew and remove some pessimism because previously you only consider the worst case and best case to find the shortest or the longest route in the graph. It's going to have a lot of pessimism. So once you identify a path, you can repropagate those values and see what are the true slew and what are the real delay value for that critical path. Or advanced on-chip variation, if you have a similar pattern that run across, for example, 4 inverter, and then the delay value is not going to be that worse, you can have another derived value to change the delay value. And that is the path-based analysis with advanced on-chip variation. Or you can remove the pessimism from the common path in the clock tree because the common path is not going to experience best case and worst case at the same time. It's the common path. The key idea here is path-based analysis, PBA, removes a lot of pessimism from graph-based analysis. Paths that had been marked failing at GPA may become passing after PBA. This is very important for preventing EDA tool from unnecessary timing optimization, okay? Because if the path is going to pass, then why are you optimizing it? PBA, path-based analysis, is very time-consuming because there are trillions of paths in a million-gate design. There is also this speed versus accuracy trade-off. The more paths you generate to reanalyze, of course, the more pessimism you can remove, and thus you get a higher accuracy of the result. However, generating more paths means higher runtime you need, right? Because it requires more computation to generate a path. So if you look at this diagram and summarize the runtime and pessimism trade-off, complete PBA is going to take a significant amount of time, even though it gives you a very good result. Okay? Without PBA, you have a very fast runtime, like a GPA, because you only consider the best case and worst case. But that has a very bad result in terms of pessimism. So the research here is we are trying to leverage the new parallelism of GPU to speed up this path generation process. So we can identify a large amount of path in a very short period of time. In OpenTimer, we use a very spatialized data structure to represent a path implicitly using constant time and space. Each path is co-represented by 2 complementary data structures, suffix tree and prefix tree. A suffix tree is essentially a shortest path tree rooted at the endpoint of a data pad. In most cases, it can be data pin of a flip-flop or the primary output. So starting from each node in the prefix tree, it leads to the suffix of the shortest path from that node. For example, if you start from node 6 over here and you follow the black edge all the way to the node 0, this is the shortest route, right? This is the shortest route from node 6 to node 0, okay? Because it's the shortest path tree. With this suffix tree, if you take an edge that does not reside on the tree, for example, like E11, that does not reside on the shortest path tree, it represents a deviation. And that deviation has a cost for not taking the shortest edge, but a detour on that edge. And the cost is positive because it detours, making it not the shortest. Each deviation represents a prefix of the tree. Each represents a prefix of a path because that's where you start deviating. So we can keep expanding the deviated path and maintain a priority queue to keep track of the top K critical path. And this criticality is defined with respect to an increasing order of slack values. More importantly, with this data structure, we can represent each path in just constant space, okay? And that is very, very important for GPU because GPU typically does not have a huge amount of memory. Right now, we are able to use a deviation, an edge, to represent a path, and that can make the design of our GPU algorithm much more efficient. Of course, this algorithm is going to work on a acidic graph, which is a spatial property of the circuit graph. So this slide shows our GPU accelerated algorithm for generating top K critical path. The text box filled with the blue represent the GPU execution, and the others represent the CPU execution. You know, for many of the EDA workload, it's not like you can just offload everything to GPU. You need to have a very good strategy to decompose tasks into CPU and GPU and make them collaborate with each other. So here we use a GPU to construct a shortest path forest or a bunch of shortest path suffix tree, and then iteratively expand the critical path candidate by sorting out the deviation from the previous level. And this process is highly dynamic. So at the end of each iteration, we send back the result, the path candidate to CPU, and use CPU to decide the next level size so we can allocate proper GPU memory for the next iteration. For example, here we have a prefix tree of deviation. Level 1 over here expands 4 deviated edges. And level 2 expands another 2 edges from the candidate in level 1. So each level represents an expansion, and each expansion represents an iteration in our algorithm. And we do this iteratively until we generate enough amount of path from GPU. So the first step in our GPU accelerated PBA algorithm is to generate suffix trees on GPU. This is equivalent to finding a shortest route ended at all endpoints in the timing graph. Here we represent a circuit graph using a sparse matrix and update the distance level by level from the endpoint to the primary input. So this process is essentially finding the shortest route, finding the shortest path. And there are many algorithms we can use to solve this problem. And for this process, because circuit graph is linear, there's no cycle, we just levelize the graph and do this with one linear traversal. And the result after this step is a collection of shortest path trees, which we call the shortest forest. Once we have a shortest path tree or the suffix tree on GPU, the next step, which is the most important part in the algorithm, is to perform path expansion to identify the top K critical path. In CPU, this is done by maintaining a priority queue over deviated edges, and we can maintain a sorted list of path candidate and pop up one path to expand one after another until we found the top K critical path. However, running a priority queue on GPU it's not very clever because The computing priority is very irregular and require a lot of synchronous operation. Instead of doing that, we leverage the power of many threads to generate many paths at one time and send back the result to CPU for ranking. And we do this iteratively. For example, here I have, three suffix 3. Black edge is on edge and red edge is not on the edge. And here I start from the first level. First level has the 3 critical paths, AEHK and BEHK, if you follow the black edge over here, and CFK. So that's the first level of the path candidate. So we send these 3 paths to GPU. On GPU, we start expanding path from the critical path we got from the previous iteration. Okay. So in this case, for example, when I look at this path AEHK, there are 2 possible deviations by taking the detour from A to D, or the deviation from H to G. And each deviation represents a particular path expanded from this critical path, right? Similarly, for the critical path BEHK, there is 1 edge possibly for us to, detour, and that is H to G. So after this expansion, the GPU thread will find out 1 deviated edge. And keep in mind, each deviated edge represents a critical path. So we keep doing this at each iteration. And this process is the key part in our algorithm. And one challenge here is the dynamic GPU memory access. Each level will expand another new set of paths. And we have no idea about the exact number of paths that will be generated at each level, right? For the general graph, the number can go exponentially. But for most of the circuit graph, like I said, the degree is not going to go beyond 10 or 12. So we can properly control the expansion size at each level. So after we find out deviated edge on GPU, we send back them to CPU and use CPU to rank the criticality to find out what will be the suitable candidate for the next expansion to reach the top K critical path. So it's very clear now, the more level you generate, the more path you have, and that gives you higher accuracy. So this leverages the strong advantage of OpenTimer's path generation algorithm. Each path is represented by a constant space, and that is the key part that we can use to store this path generation to GPU. We can control the memory complexity to be linear on GPU. Now we have introduced our GPU accelerated algorithm for generating critical path. I'm going to show you the result. We implement our algorithm in C++ on the same NVIDIA RTX GPU and 40 Intel CPU. Because this algorithm iteratively expands the path level by level, the accuracy is highly related to the number of levels you expand. And we use the term MDL to represent the number of levels we expand in our algorithm. And again, here is the execution parameter for our GPU kernel. Well, this slide shows the overall result that compares our runtime of 1 GPU with OpenTimer of 1 CPU. Apparently, the more levels you expand, the higher runtime we need, even though it's only a tiny difference. We can achieve very large speed up on this process, especially for large design. For example, in design Leon 2, that has 1.3 million gates, we are about 600x faster than OpenTimer. And on another large design that compose Leon 3 MP, they compose about 1.2 million gates. Our algorithm is about 200 faster than OpenTimer.
Now, I have a question.
Sure.
So because there is the Open STA around there. And they also do the worst path pessimist. How you compare the time and the accuracy? Both of them are open source. Now you can compare. It's not like runtime.
You mean runtime or accuracy?
Both.
Yeah, we compare both. The accuracy is strongly correlated. For most of the path, the traces are the same. We can output pretty much the same result as OpenSTA, but the runtime is significantly different because the OpenSTA does not have, very, I guess, not very good algorithm for generating a path. So it takes several hours.
Okay.
Yeah. And we do not report the value comparison with OpenSTA because the OpenSTA is, even though it's open source, but it targets on commercial use. So it deals with lots of user side components that also contribute to the runtime overhead. But according to our offline experiment, even the CPU-based runtime in OpenTimer is already faster than OpenSTA, several orders of magnitude. Okay. So this slide summarizes the accuracy versus levels in our algorithm. More GPU expansion, more GPU iteration will give higher numbers of paths and thus better accuracy. For all the benchmark we have tested, using about 10 iteration can produce already very good result. Pretty much, match all the golden solution generated by OpenTimer and OpenSTA. Of course, the number of levels you expand is depending on the capability of a GPU. If you have a very large global memory on GPU, then you can have more expansion. Based on what we know, most GPU can handle 10 levels in no problem, and 8 GB memory because our algorithm takes only constant space for each path. And this slide compares our runtime with OpenTimer at different CPU numbers. In our algorithm, we always use one CPU to collect the result from GPU at each level. So increasing the number of CPU does not change our runtime, but it reduces the runtime of OpenTimer because OpenTimer has many core CPU parallel PBA algorithm. So the more CPU we use, the faster runtime OpenTimer finishes with. And we can see the runtime of OpenTimer saturates at about 16 core. And this is quite consistent with most of the existing timer. When you go beyond scalability, typically stagnate beyond after 16 core. There's no more scalability you can get beyond that. However, if you look at this trend, there is always a huge gap between our algorithm and OpenTimer, regardless of the number of CPU you use. And our algorithm of one GPU is even faster than OpenTimer with 40 CPU. For example, on Leon 2, we are 44x faster. Leon 3, and there is another very large design of 1.2 million gates. Our algorithm can finish the PBA in 25x faster, and same for the other large design. In fact, according to our experiment, our GPU-based PBA algorithm is always faster than OpenTimer's CPU baseline, no matter how many CPU cores you use. So finally, I want to end up the talk with the following concluding items. We introduced the runtime challenge of STA on two parts. We know what the graph-based analysis is and why it is challenging, and what are the critical part, what are the most time-consuming part in graph-based analysis. We also do the same thing for path-based analysis. We introduced a GPU-accelerated algorithm to speed up the graph-based analysis compared with the OpenTimer that is highly CPU parallel GPA algorithm. We can achieve 4x speed up on large design. And when it comes to the acceleration of PBA, which is more time consuming, the speed up value is even more promising. For example, we can achieve 600x speed up on large design. And this GPU acceleration idea has lots of new opportunities to change the way we design and run EDA tool, based on my humble opinion. Often, the speed up is deterministic and more explainable, right? You have a design algorithm on the GPU, and you can easily explain why there is such a performance gain. And there are still many research topics we can do, and we are doing, and we are trying to do to accelerate CAD many other EDA algorithms through new parallelism on GPU. Some of our future work will focus on designing GPU accelerated incremental timing, or designing load balance PPA algorithm on GPU, or leverage modern GPU graph parallelism to incorporate different delay models and gate and RC delay and so on and so forth. With that, I'm going to stop here. I think I control the time very well. So thank you very much. I'll be glad to take any other questions.
Yeah, do we have any questions from any of the students or anyone attending? You can raise your hand. We know most everybody, so I'll give you voice access if you want to ask it, or you can chat it.
While the students are thinking, on the CPU, you were showing not much scalability, like 2 slides back.
Give me a second. Yes.
Yeah, here. So here, I was thinking that it will scale better because I thought that you have many paths, and then you have to do the worst path pessimist to analyze each one of the paths. So you can analyze each one of those paths in parallel. So as you provide 100 paths, you should be able to occupy not 100 CPUs because might have different time each one of them, but should scale quite well. So how come it's not happening something like that? What I'm misguessing here?
Well, I think this scalability issue has many reasons. And one of the results we found that CPU-based parallelism does not scale very well is because when you analyze this timing, when you analyze the path, it's very irregular. And you are going to have a lot of load balancing issue. And most likely you are not going to saturate the memory, you're not going to saturate the memory in a very efficient way compared to GPU. And that's why one of the key reasons why, if you look at this CPU-based parallelism, most of them do not go beyond 16 cores. Do not go beyond 16 cores.
So it's bandwidth bound.
Yes, yes. And also analyzing this path is very irregular. It's very irregular. So unless you have a really efficiently designed data layout, otherwise you won't be able to maximize the the benefit.
My questions are, I guess, very similar to Jose. I'm trying to understand if the fundamental scaling limits you're running into here. I think this is very interesting. I have these two kernels you're looking at, the PBA versus the GBA, and they both have different, ratios in performance between optimized CPU versus optimized GPU, right? And so, can you maybe shed a little bit of light about how for the GBA problem, the GPU benefit was much less? Is that because the CPU is doing a much better job of being utilized? The GPU having a harder time with convergence or divergence or something, or what's going on?
I think one of the key difference between GBA and PBA is the data size, because when you run GBA, you do not have too much data size compared to PBA. In PBA, for example, here we request, let's say 1 million path, and you need to analyze a huge amount of data across this 1 million path. But in GBA, we only consider linear graph-based update. So we do not have too much data. And then that's why on GPU, we don't have this significant benefit, but still run faster. It's still much faster than CPU.
Sure, but you're saying from the CPU version, maybe benefits from like cache locality or something, you'll be able to get better runtime?
Yes, that's true.
Neat. Thank you for your talk.
Thanks for the question, by the way.
All right. I don't think we have any other questions from students, but yeah, thanks for giving the talk, and we appreciate it.
Thank you. Thank you.
So I have some questions.
Okay.
I don't know if you guys, I don't want to keep everybody late. I was just waiting to make sure that everybody else got theirs asked. No, this has been awesome. And, I did some previous work on GPU graph algorithms, and coming at it from more of a programming language side, and this goes to your related work, from a programming / compiler point of view, it would be awesome if we had a framework that you could use where you didn't have to think about load balancing, where you didn't have to think about memory transfers or coalescing, and you could express the algorithm at a high level.
Exactly.
And we're trying to, well, there has been some approaches to do this. There's like Graph Blast, there's Gunrock out of UC Davis. And I'm just wondering if you have thoughts on maybe where those approaches have fallen short, or if you plan to use them in the future, stuff like that.
No, indeed, that's one of the innovation in OpenTimer, because like you say, one of the, when we start working on this, one of the factors that affects the performance significantly is the load balancing. Because when you levelize this graph, you are going to propagate the timing level by level, even though you can run the timing in parallel for each level, but you suffer from a lot of this load balancing issue. So we think it might be a much better idea if we can come up with a framework to describe everything in, for example, a task graph, right? Such that we can have separate concern. You just focus on describing your propagation task and build out a dependency using this programming model and library, while leaving all the scheduling, dynamic load balancing detail to the library itself. And this is one of our research project on task flow. And we do propose a programming model that is particularly designed for this kind of workload. So the entire OpenTimer right now, including our algorithm I presented today, is built on top of the task-based framework.
Very, very cool. And do you know how that framework relates to kind of other frameworks? Like there's like Graphit, there's Ligra, there's Gunrock. Did you look into those at all?
Yes. Initially, before we develop our own task graph library, we try a different, existing model and framework from the scientific computer community. Like, I mean, there are too many, like Coco's OpenMP task graph, or Parsec, or there are just too many task graph parallel computing framework. And one of the problem we found is there are two limitations. The first limitation is those task graph computing framework are based on direct acyclic graph. They cannot handle control flow. But if you look at the algorithm we are dealing, for example, this slide, it's iterative, which means it's not like you can just describe the entire graph in just one, entire workload in just one graph. You are going to have a lot of control flow. So if you are not going to model the control flow into the graph, then you are not going to achieve end-to-end parallelism, and affect the performance very significantly, especially when you send back the data from GPU to CPU, right? And you're going to synchronize everything, and you don't have the dynamic load balancing to overlap those data movement costs with the computation. And that's the first problem when we try to use existing framework. And the second problem is most of this task graph computing framework, they do not scale to like millions of tasks, because in our workload, circuit graph is very, very large. It's very, very large, and it takes a lot of time to compute. If you describe millions of tasks across the timing graph, most of existing framework will fail. That's based on our experiment.
Yeah, I might interject for a second, because I think Tyler asked a different question. So I want to make sure we're connecting dots here, because I think you give a great explanation about the task graph programming models, right? For people trying to do generalized parallel programming using task graphs.
Yes.
I think Tyler perhaps maybe was asking more specifically about graph frameworks for graph data structures, things, let's say, suggested things like Gunrock, right? Which is like a very specific, graph framework for GPUs. And so I think that's something that's interesting for us on the graph HPC side, is making sure that, we're proposing graph specific, not so much parallelism, but graph specific APIs that are usable for application users, right? So if you use an application user, look at GraphBLAS or Gunrock and say, that's not flexible enough for me, that's a problem for us, right? And so, for example, in my case where I wrote some graph transformations for my CAD tool, I'd written some C++ stuff. I hadn't really been so formal to have a strict API. I kind of wrote graph algorithms OpenP to whoever I could do them as fast as I could. And then doing a similar thing in Scala for my persistent CAD tool. But I think Tyler may have asked more specifically about certain graph frameworks. Did you actually try out, or at least consider things like GraphBLAS or Gunrock or something like that? Or are you just a Graphit MIT, DSL?
We do try GraphBLAS, and we actually use it in our levelization, levelization GPU kernel. And we do not use for example, GraphBLAS on other part. Is if you look at this timing application, many of the GPU computation is very application specific. So we often need a lot of flexibility on the data. We need to design spatial kernels and based on spatial property of this timing property to design the kernel. And when we use those libraries, they do not have, some of them have too high-level abstraction that prevent us from doing detailed memory layout optimization and things like that. That's one of the biggest issue we found. But for levelization, this kind of task, we use a graph blast.
Oh, neat.
Yeah. So I would say unless those library provide some interface that can make application develop more easily, especially for people like us, because we need a lot of domain-specific knowledge to design GPU kernel. And abstraction is good, but too many abstraction may not be helpful.
Yeah, no, that's really interesting. And I might follow up with you
yes.
after the talk, because I'm very interested in trying to think about better abstractions to help people working on concrete use cases like you've described.
Yeah. At least for our application, data abstraction is not as important as task abstraction, because people in our field, they are very good. They want to handcraft detail of the data, because many of this data has to be optimized based on our domain-specific knowledge. But we don't want to deal with like scheduling, load balancing, those kind of task level scheduling details.
So I have a question about the levelization, because I use something similar, like a topographical sort. Do you have the CPU version of the algorithm by multi-core?
No, we do not implement CPU levelization.
Levelization
is, yeah.
So you only have it in the GPU. You
yes.
only have that code GPU based.
Yes. And this levelization can be very time consuming. Depending on the size of the circuit graph.
But the results that you were showing, it really reduced a lot of time when you were doing the GPU.
Yes. If you look at this runtime breakdown, we can reduce it.
So the code for this is already on the OpenTimer on the website? Because I just quickly
no, not yet. Not yet.
Okay, I looked for it. I couldn't see it.
Yeah, we are thinking about to have all this GPU capability in OpenTimer v3, and like I say, if we want to make the whole thing GPU friendly, we need to redesign a lot of this data structure. Otherwise, it will be just incremental update on the existing code base.
Okay. Now, because to understand the levelization, I was expecting not to scale so well, because every time that you do a level on the GPU, you are going to have a barrier, some sort of atomic operations when the nodes converge.
Yes.
So I'm guessing that your graphs expand very fast, and they don't have much overhead on those atomics. Or do you?
We use
a structure is a data race free or something, or how do you do that?
You mean how to avoid the overlap, or
yeah,
you have an atomic variable to decide. For example, if you look at G and H, they all touch the same node E, and we use atomic variable to check whether this node has been marked already in this level.
But then it means that every access that you update for the next, you have to assume that it's a potential conflict. So all the access have to be atomic.
Yes, and that is why we do not do this. We do this backward, not forward. Because if you look at the distribution of the input degree and output degree, they are very, very different. For example, if you do this in forward, you are going to suffer from a lot of these atomic, assets at the same time. That hits the performance, that hampers the performance. For example, in this design, the maximum output degree is 260, and it comes from a very large RC network, which means you may have 260 threads touch the same node at the same time. And so we do this backward, and that's also one of the motivation we are trying to avoid too many atomic operations.
Okay.
Yep. And this simple strategy helps improve the performance by 15% based on our experiment.
All right. Well, thanks. So with that, we'll call it a day.
Thank you. So I appreciate all the questions from the
Thank you.
panelists. And if you have any questions, you can always send me the email. Thank you.
Thanks.
Thanks.
Thank you.